Hello and welcome to this session, Learning Outcome LO5. Understand simple nuclear and atomic physics. Today we will learn what makes up the universe at its most fundamental level. We will explore the principles of nuclear and atomic physics and see how they explain processes such as energy generation, medical applications, and much more. Atoms are the building blocks of matter, consisting of a nucleus and electrons. The nucleus contains protons and neutrons, held together by a strong nuclear force. Electrons orbit the nucleus in energy levels or shells. The number of protons defines the element, while neutrons determine the isotope. Atoms become ions by gaining or losing electrons. Ions form when atoms gain or lose electrons, resulting in a net charge. Isotopes have the same number of protons, but different numbers of neutrons. Some isotopes are stable, while others are radioactive. Carbon-12 is stable, whereas carbon-14 is radioactive and used in dating. Understanding isotopes is crucial in nuclear physics. Radioactive nuclei emit radiation to become stable. Alpha, beta, and gamma are the three main types of radiation. Alpha particles have high ionizing power but low penetration. Beta particles have medium ionizing power and penetration. Gamma rays have low ionizing power but high penetration. Half-life is the time for half of a radioactive sample to decay. It is constant, unaffected by external conditions. Some isotopes have short half-lives, others last thousands of years. Half-life helps date rocks, plan medical treatments, and manage radioactive waste. Understanding half-life is key to nuclear applications. Nuclear fission splits a heavy nucleus into smaller nuclei, releasing energy. It's used in power stations, submarines, and weapons. A controlled chain reaction generates heat for electricity. Fission is powerful but produces radioactive waste. Understanding fission is essential for energy production and safety. Fusion combines light nuclei to form a heavier nucleus, releasing vast energy. It powers the sun and is cleaner than fission. Fusion is efficient but challenging to control on Earth. It requires extreme temperatures and pressure. Mastery of fusion could revolutionize energy production. Nuclear physics has diverse applications, from medicine to energy. Radiotherapy treats cancer. PET scans aid diagnosis. Industry uses nuclear techniques for material measurement and leak detection. Nuclear power provides low-carbon energy. Understanding these applications highlights the importance of nuclear physics. In modern physics, forces arise from particle interactions via exchange particles. These short-lived particles carry momentum and energy. They enable interactions at the smallest scales, known as gauge bosons. They are crucial to understanding forces. This concept is foundational in quantum field theory. 4 fundamental forces govern the universe: electromagnetic, weak nuclear, strong nuclear, and gravity. Photons mediate electromagnetic interactions. W and Z bosons carry the weak force, responsible for radioactive decay. Gluons mediate the strong force, binding quarks. Gravity's exchange particle is theoretical, known as the graviton. Exchange particles explain forces without physical contact. When particles interact, one emits an exchange particle, which the other absorbs. This transfer changes momentum, interpreted as force. This model matches experimental results and underpins the Standard Model. Forces arise from virtual particle exchange, not visible pushes. Particle interactions must obey conservation rules. Charge, baryon number, and lepton number must remain constant. Energy and momentum conservation apply to all interactions. Strangeness is conserved in strong interactions, but not always in weak ones. These rules ensure the balance in particle physics. Charge conservation means total charge remains unchanged in interactions. Baryon number conservation ensures baryons and antibaryons balance. For example, in beta decay, charge is conserved. In proton collisions, baryon number remains constant. Understanding these rules is fundamental to particle physics. Lepton number conservation applies to electrons, muons, and taus. Each has its own family number, conserved separately. In beta decay, electron family numbers balance. Antileptons have negative lepton numbers. These rules are crucial for validating particle reactions. Energy and momentum must be conserved in all interactions. This includes rest mass energy, described by E equals mc squared. Reactions that create energy are not allowed. Pair production illustrates momentum conservation. These principles are vital in understanding particle behavior. Strangeness is a quantum number in particles with strange quarks. It is conserved in strong interactions, not always in weak ones. For example, in K- reactions, strangeness is conserved. Understanding strangeness helps validate strong interactions. These rules are key to particle physics. To validate reactions, check charge, baryon number, and lepton number. Also, verify energy, momentum, and strangeness for strong interactions. For example, in muon decay, all rules are checked. This ensures the decay is allowed. These steps are essential for understanding particle interactions. Decay curves show the number of undecayed nuclei or activity over time. The decay law is exponential, described by n equals n naught e to the negative lambda t. The decay rate or activity decreases as n falls. This pattern helps calculate decay rates and half-life values. Understanding decay curves is crucial for radioactivity studies. Half-life is the time for a sample's nuclei or activity to have. From the decay law, half-life is calculated using lambda. On a graph, it's the time for count rate to have. Repeating the process checks consistency. Knowing half-life aids in understanding radioactive materials. Half-value thickness reduces intensity of gamma or X-rays by half. It's described by I equals I naught e to the negative mu x. The graph helps find half-value thickness. This concept is key in radiation protection. Understanding absorption is vital for safety measures. Excitation occurs when an electron absorbs energy and moves to a higher level. Ionization happens when an electron gains enough energy to leave the atom. Photons or electrons can cause both processes. These interactions are fundamental in X-ray production and lasers. Understanding excitation and ionization is crucial in atomic physics. In conclusion, mastery of nuclear and atomic physics is essential for driving technological progress and advancing scientific innovation. Have questions? Drop us a WhatsApp message at 0748436168 and a team member will get back to you promptly. See you at the next session.